All right, welcome back to the drive-through. Hungry? Stop by the deli. Make yourself a salami roll-up with veggie cream cheese and hot sauce inside of some Genoa salami, if that's how you say it. Okay, this is number 57 from 10.6. Some actual calculus to be done here. Okay, they say the curve z equals 4x minus x squared in the xz plane is revolved around the z-axis. So let's sketch that, which is going to be hard. Okay. Well, we got our x, our y, and our z. Hopefully you guys recognize this as a parabola that's upside down. Okay. And since we're revolving it around, revolving it around in the xz plane, Hold on, I'm doing that wrong. It's going to look something like that, okay? It's revolved around the z-axis. So over there, you're going to have like a matching curve, if you will. And all of those points are going to be revolved. And so if you can imagine what this is going to look like, it's going to be a bundt cake. Do you know what a bundt cake is? I'll do a better job of sketching that in a second, okay? All right, so first, the simple calculus, the shell method. Shell method is defined as volume as 2 pi times the integral of x times f of x dx. Some of you knew that. Some of you went back and looked it up. I don't think any of you, and this is not a knock on anyone because I didn't really know it until I thought about it, I don't think any of you really understand why this gives you volume. So that's the point of this little exercise. But first, let's just do the calculus, okay? So the calculus would be 2 pi. This intersection point right there is 0, 0, 4. Well, actually, no, sorry. I'm all backwards. 4, 0, 0. Think about it. That's where that is going to hit the axis. So our bounds of integration are going to be as x goes from 0 to 4. Okay? And then we write down an x. Our function is 4x minus x squared dx. So all we've done there is just successfully plugged all of our information, bless you, count it, into the shell method. Okay? So we'll do some quick calculus just so we can refreshen our calculus skills. Anybody? Yeah, 4/3 x to the third minus. Yeah. Okay? And then you plug in, sorry, that should be this. You plug in 4 for x and you get a common denominator, and I'll save you some time. You get 164 pi over 3 units cubed. Okay, that's our answer. That's the calculus. Let me check to make sure that's right. It is. Okay, now let me redraw this. I hope everyone can understand that we can. Is it 128? I didn't even look. Indeed, it is. 128, sorry. 128 pi over 3 units cubed. All right, now, hopefully we can all agree that we could do this same problem, but it would be easier to graph if I would rotate it around the z-axis, so I'm going to do that. Okay? I need a nice parabola so I get a nice bundt cake. Okay. Do you know what a bundt cake is? It's a cake pan that has like a almost like a one of those things in the middle that you would put your penny in at the museum, and it goes around forever really fast. Okay? So think about this. I want you to think about this. Our x value, how far we go in the x direction, that's going to determine the little radius of rotation. So all these little points are going to be rotated. However far we go in the x x direction. Now here, look, this will be a big radius of rotation. So maybe, just maybe, you can start to kind of envision this bundt cake looking thing, and it's like, the pan looks like this. Maybe you've seen one of those, maybe you haven't. This part in here is hollow. Okay? Alright, now look. Here's what I want you to understand. When you first learned about volume, okay, you learned about the volume of a rectangular solid, or maybe even a cube. That was first. It had a length, a width, and a height. So anything with volume has 3 dimensions. Okay? If I go back to the 2-dimensional sketch of this thing, I want to try to explain to you guys where this equation comes from. Okay, so the x value is that. Okay? What that determines is the length of the radius that's being rotated. Can you buy that? Okay? So we are going to call that the radius. F of x is the height of the cylinder, okay, at that point x. So we are going to refer to that as height. Okay, now, you might recognize 2 pi RH. Do you recognize that? That is the lateral area of a cylinder. I want you to think about a piece of paper here, and I'm holding it sideways. What shape is the paper? It's a rectangle. Okay, now I just folded it into a cylinder. Okay? What's the circumference of the cylinder? That's 2 pi r, right? That's the length of the rectangle. The height of the cylinder is the height of the piece of paper. So the lateral area of this cylinder is 2 pi RH. So what I went to Mr. G and said was, it seems like we're adding up surface areas and getting a volume. And that doesn't make any sense to me geometrically. And so I interrupted him during his class, and then we said, okay, we'll talk about this later. And then he came back, and we started, because what I really was asking him was, how do I interpret this dx? Okay? In my mind, if you add up all the surface areas, it gives you the volume. But that doesn't really make a whole lot of sense. We're adding a bunch of 2-dimensional things and finishing with a 3-dimensional result. Here's what we came up with on, here's what Mr. G came up with, basically. But I do feel like I helped a little bit. All right, now look. The adding of all the things, that's what the integral does. Do you guys get that? We're adding up a bunch of really little things. That's what integration does. The 2 pi, you can kind of forget about from a calculus standpoint, because we just factored that out. It was just a constant. Okay? And the 2 pi is more of a geometric thing of how we get from the radius to the circumference. Are we comfortable with that? Well, here's what the dx does. Originally, what was the dx? It was a delta x, right? And that was, instead of considering this thing to be a shell, consider it to be a solid. That thing has volume now. It doesn't just have surface area. Can you envision that? And this thing right here is delta x, right? And by definition, our integration takes place as this delta x approaches what? As it approaches 0. Okay? So, by putting the dx there and putting the integral here, we've allowed the delta x to become basically infinitesimally small, but we're adding up all of those volumes. These are now volumes because it has a delta x. And now it makes way more sense to me. We're not adding up surface areas. We're adding up volumes. And you can think of that like your skin. The cell of your skin is infinitesimal. It has no width. The cell doesn't. But eventually it builds itself layer upon layer upon layer. And now it has volume. Your skin does have a thickness. And that is why the volume of the shell method has that formula. That's the whole point of this class, is that we kind of figure out why this stuff works, because we can take our time and do it. Got it? Does that help? Boom.